integrals of unbounded functions, not to confuse with unbounded interval. The integrals of unbounded intervals are of type 1, and the integrals of unbounded functions are of type 2. So this is the type 2 improper integrals. Suppose that the graph of f has an x equals b as a vertical asymptote, and that for a fixed, f is integrable on the interval a to t for all t in a, b. They have closed interval. If a limit t go to b from the left-hand side of the integral from a to t f of x dx exists, we will say that the improper integral from a to b of f of x dx is convergent, and we define the integral from a to b f of x dx as the limits at t approach b on the left-hand side of the integral from a to t f of x dx. Similarly, if x equals a is a vertical asymptote, then we define the integral from a to b f of x dx equals the limits at t approaches a from the right-hand side of the integral from t to b f of x dx if the limit exists. Notice that the function is unbounded at these vertical asymptotes. For the first case, there is a vertical asymptote at x equals b. Thus the function is unbounded at x equals b, the vertical asymptote. And for the second case, the function has the vertical asymptote at x equals a. With the vertical asymptote on the right-hand side, or at the upper limit of integration, we would need to approach the vertical asymptote from the left. With the vertical asymptote on the left-hand side, we would need to approach the vertical asymptote from the right-hand side. The notation superscript minus sign in the limit indicates that this is the limits at t approaches b from the left-hand side. T approach a plus, meaning t go to a from the right-hand side. These are known as the one-sided limits. If the function f of x has the vertical asymptote x equals c inside the interval a comma b, then the improper integral a to b f of x dx can be rewritten as the limits at t go to c from the left-hand side of the integral from a to t f of x dx plus the limits at t go to c from the right-hand side, the integral from t to b f of x dx, although the two t values are not the same. It is better to use different letters, such as p and q. For example, for which values of r is the integral 0 to 1 x to the r dx convergent? If r is greater than or equal to 0, then x to the r is a continuous function on a closed interval 0, 1, and the integral exists. For example, the integral from 0 to 1 of x dx, the integral from 0 to 1 of x to the 1/2 power dx, those integrals exist. If r is negative, then the limit at x go to 0 from the right-hand side of x to the r is infinity. Thus, this is improper and we have to take the limit. We have the limits at t go to 0 on the right-hand side of the integral from t to 1 x to the r dx equals the limits at t go to 0 on the right-hand side of x to the r plus 1 over r plus 1 evaluated at t to 1. This is 1 over r plus 1 times the quantity 1 minus the limits at t go to 0 from the right-hand side of t to the r plus 1, provided that r is not equal to -1. If the exponent r plus 1 is positive, that is, r is greater than -1, then we have the limits at t go to 0 on the right-hand side of t to the r plus 1 equals 0, so the integral is convergent and is equal to 1 over r plus 1. If r plus 1 is negative, that is, r is less than -1, then the limits of t go to 0 on the right hand side of t to the r plus 1 is infinity, so the integral is divergent. With the case r plus 1 equals 0 or r equals negative 1, this integral is 0 minus ln of t, and as t go to 0 from the right hand side, ln of t go to negative infinity, that the integral is divergent. Thus, this integral 0 to 1 x to the r dx converges only when r is strictly greater than negative 1. If we write x to the r as 1 over x to the p, then p equals negative r. Thus, the integral from 0 to 1 of 1 over x to the p dx is convergent if p is less than 1, and it converges to 1 over 1 minus p, and it is divergent for p greater than or equals to 1. This is called the p integrals, and we will be using these often from now on. For example, the integral from 0 to 1 of 1 over the square root of x dx, we know that this is convergent because p equals 1/2 in this case, which is less than 1, convergent. For the integral from 0 to 1 of 1 over x to the 5/2 dx, we know that p is 5/2 in this case, which is more than or equal to 1. Therefore, the integral is divergent right away without having to evaluate them.